All right. I really hope that people can hear me because I have no feedback, or maybe can just have a look on my phone. So, also, if you can give me an okay whether you can hear me, that would be great. Just in the chat, maybe. I think that's gonna be all right. Just start my PowerPoint presentation. Starting with my last slide, of course. Perfect. Cool. So I must admit this whole YouTube thing is completely new to me. And so it's even more novel for me instead of talking in front of Zoom because I don't see you. But anyway, yeah. Bonjour, mesdames et messieurs. Je m'appelle Benedict et j'ai un chercheur d'Allemagne et je vais te présenter des well, I think I switched back to English. I should have prepared myself a bit better in terms of French, but anyway, today I'm gonna show you some of our recent advances from UC2, which is one part of our frugal commitment to make microscopy available to everybody. So the talk is structured around the idea of changing paradigms, science for a dime. So I'll give you a few details how this could eventually look like. And everything what you see here is completely open source. So most of the stuff is already documented and is somewhere in GitHub. So it's just the question where to find it. So whenever you have a question, write it in the chat or just write me an email afterwards. I would be very delighted to help you out to spread the word. Right, let's directly dive in. So I think most of you, I cannot rely on your feedback right now, but everybody mostly knows what this is. It's a hammer. And I think also everybody knows how to use it. So you have a nail, you hammer it, and that's done. When it comes to microscopy or optics in general, it's very difficult to understand what's happening there. So I just took two random images. I think the first one is a rendering. The other one is actually a physical setup where you try to measure quantum properties from light. And well, it's not directly correlated to microscopy, but I think it's very difficult to replicate either of those. And so for me, even though I'm in the field of optics for quite some time, it's very difficult to replicate those setups. And that means for me, they appear to be a black box. And that's not good because I think in science, we need to be able to replicate progress so that we can build on top of each other's findings and also accelerate science, etc. And then you have the problem of eventually users and developers somewhat split up. So in best case, they can join forces, work together, and also create truly interdisciplinary science. And I think microscopy is just a very nice tool to do so because you can form groups, you build on joint projects and make nice findings in the end. It's definitely possible, but the problem there is if you look around, I think there are lots of different commercially available microscopes, for example, a light jet you can just buy or structural illumination microscopy, but all of them somehow have at least one problem. And I just identified a few of those, being affordability, accessibility, adaptability, and also the availability. Funnily, everything starts with an A, maybe the 4A principle. But there should be ways to solve these issues. And luckily, there has been some work done by many people in the open source community. I apologize for the slide, it's somewhat distorted. But anyway, so there's, for example, the OpenFlexure from Richard Bowman's group. There's the MyCube from Johannes Holbein, and there's also the Squid or Octopi and the Full Scope from Manu Prakash, where I'm working on right now. But there's also some image processing tools, like, for example, Fiji, I think most of you know, and also ImpJoy. And so there's a huge cosmos of available tools. You can just use progress your research for which basically solves these issues of availability, in most cases also accessibility or affordability. The key to most of these instruments is to find alternatives. So especially if you're keen on pushing the price. So in most cases we are somewhere in the lower bar, and the price is still wrong, but I think this is a good example, because spending roughly the amount for a camera, like the EMCCD camera, easily costs in the range of 10 to 20,000 euro. You could eventually also get a camera that's less expensive, like one from a cell phone, or maybe even one from the Raspberry Pi. And so usually, I or our group tries to focus on these devices so that it's really becoming cheap and also available, because these motors you can literally get everywhere and almost independent from any chip crisis. And so, in the end, it's always a matter of, how can you use these devices, because most of the time they don't come with the datasheet, and also it's a bit more difficult to interact with them. I'll give you an example how this could work. So in case of this optical pickup device, you have to see on the very left-hand side, it's a perfect device for single-mode fiber coupling, for example. And the way these optical pickups are used, usually is you have your optical drive, and it's rotating, and on this CD or DVD or even Blu-ray, the information is embossed or burned into this disk by means of zeros and ones, and you read it out optically. So you have a small optical system that's just detecting whether there's a refraction or not, and they do that refraction limited, so that it has to be very precise to have a good point spread function, going down to 250 nanometers in case of the Blu-ray player. That means you have to be in focus all the time, and you have to really find this very pitch on the film here. And so for this, the whole optical system is insanely complicated, but built on a very large scale. So you fabricate millions of these devices, hence they become super cheap. And we can make use of those, because there's a very important thing. It's the objective that's mounted in an optical assembly that can do focusing and also aligning of the optics inside a voice called motor-driven assembly. And we can just simply interact with that, here shown with a very similar setup from an autofocusing lens from your cell phone, but just simply connecting an Arduino to it and focusing the light and steering the lens. And this becomes then very useful, because when you have access to yet another cool technology called Nanoscopy on the chip, it's coming from a group from Norway, from Volprinting and Øystein Helle. You can do super resolution on a very compact and also low cost scale. So how does that work? So you have a small photonic chip that's usually made out of silicon. It's the substrate, and then you structure a very high refractive index material on top of this chip, for example, in the shape of a simple slab, which is only 150 nanometers high and roughly 15 micrometers wide, so it's much more wide than high. And then what you do is you focus light into this slab, and then when you have a cell that's fluorescently labeled sitting on top, it's basically illuminated from the total internal reflection, or like the evanescence field from below. So that means you have a turf microscope, or you can realize a turf microscope on any microscope out there without any fancy turf optics. Yet the problem there is, how do you get the light into this 150 nanometers thick sheet? Well, I'll tell you in a second. First of all, to really realize super resolution microscopy, you also have to have a look what are the most important aspects, where can we save money and also scale it up so that everybody has access to it. And I think, as I said, the camera easily costs between 10 and 20,000 euro. In this case, it's an EMCCD from Andor. And the first naive approach was really just replace this camera with your cell phone. And so we attach the cell phone to the eyepiece, and what we then try to do is capturing D-storm data, or single molecular localization data, where you instead of having spontaneous emission from your fluorescent emitter all the time continuously and obey the formula von Abbe, so that you are roughly limited by a factor of 2 in terms of resolution compared to the wavelength. You just increase the illumination wavelength and add a proper imaging buffer so that this the fluorescent dye eventually not only enters the singlet state, but the long-lived dark state, or after entering the triplet state. And with that, it's possible to not have a continuous emission of your fluorescent sample, but rather a blinking, which you see here on the right-hand side. So with this, the resolution per se is not improved at all, but you can do statistics on this video stream now. So what you do is you localize each of these little blinking events, and then with that you have a table with many events, and you render them over time, so to say, so that you in the end have, for example, the actin structure of these cells here that are fluorescently labeled reconstructed, and then you are not limited by the classical Abbe formula, but rather by the number of photons you can detect. And this was the very first result on the cell phone. So this is the EMCCD camera, and this is the cell phone that achieved a resolution on around 80 nanometers. So, but the problem is still you need this bulky setup, and the next step would obviously be, how can we miniaturize that? And I told you about the waveguides, and so we built a small microscope around these waveguides called CellStorm 2 that captures the fluorescent response from your coupled light, which is sitting in the waveguide chip. So you have this cell phone, you have a small optical train here. It's basically just a finely corrected microscope with a detection lens here. You couple the light by basically or simply just taking your laser, focusing it into this waveguide, and tuning the focus with this optical pickup unit. So that's what you see here. There's the pickup unit, and the red slab here is the guided light in this chip. And then you can do all kinds of cool imaging scenarios. For example, these chips come from Norway, and this is very an analogous way to do the imaging there. So when you wiggle around the lens here, you basically wiggle around the static mode pattern inside this chip, because it's single mode along this very one direction. Since it's just 150 nanometers high, only certain waves can resist in this chip. And when you wiggle it around, you get this kind of structured illumination. And from this, you can reconstruct higher frequencies from the object that usually are not visible. In this case, it's some membrane-labeled E. coli bacteria. This would be the bright field response as the sum projection from what I just told you, or showed you. And this is then the reconstruction using algorithms, for example, like SURF, etc. And you can achieve 150 nanometers even with living cells. I think that's pretty cool. So this, I think I'm going to show you in a bit. And then we were asking ourselves the question, so this project is already a little older. So we built a setup during the pandemic, and then people were approaching us and were asking, could you eventually also resolve the virus itself? And then we were thinking, yeah, well, theoretically that would be possible. And we took one of these microscopes, we would just build it and literally put that on our bikes, drove to the high safety lab, and we imaged a few of these viruses, which you can see here on the left-hand side, in this BSL-3 lab. So it was a really interesting experience to be there as a technician. And then later reconstruct the virus. So you can identify the virus by its size. So here's just antibody labeled viruses, and then the reconstruction you see here on the right-hand side. And then the advantage is that you can reconstruct these viruses on a very large field of view. I think in terms of testing, that's definitely not possible because it takes very long to label them, but it's definitely an interesting approach. So right now I'll make a little cut because I'll dive into this whole field of UC2. And so my background is more oriented around electronics. So in 2006, I did my apprenticeship or apprenti in electronics, and I had this task many times. So I had to develop a PCB with a certain functionality, and it usually took ages to get a single LED to blink. And what came out there when I was done is this Arduino. And I hope everybody had the chance to work with that at least once, because it's really fun. And you just plug it into USB, it's starting to blink in the very moment. And the cool thing about it is it's community driven. So you have lots of code available and you can start crazy projects instantly. And when I joined Rainer Heinzmann's lab, where I'm still working right now in Jena, I was facing a very similar problem with prototyping optics. And I was thinking, okay, you always have these setups here, which are already in a way very modular, so that you have a light source, lenses, objects, objectives, and a camera, and they follow this so-called Fourier optical principle, so that the focal lengths are following one another based on the optical setup here. And this is very nice because then you can just start drawing boxes around it and modularize your optical system. And so from this, we started then to get creative with blocks, or not quite so, because we are starting with prototyping optics with 3D printing. So the initial idea was building a small incubator microscope where you just observe some cells. So we started with some naive approaches, and you already see, like, after some time, we decided, okay, it's so much more sensible to have it modular so that you can reuse your components. And now we're at a state where you have a bunch of modules, and you can just choose from a library similar to Python, where you just import your modules and you just make use of existing solutions, so to say. So, for example, we have also adapters for the open flexure stage or XYZ stages. We have lasers, etc. And when you have that, you can just construct arbitrarily complicated setups. For example, starting with a simple one where you just have inverted microscopes for observing cells. And so you can place many of these because they are relatively cheap inside incubators. And okay, I just get a message. We don't see all pictures in OBS. Click on screen capture and I hope you see me. Yeah, okay, my cell phone sees me. Sorry for the interruption. Right, so you can place many of these in the incubator, and then you're all set. So anyway, so you can add more complexity to your setup by, for example, swapping or like introducing more complicated components. This is, for example, an example for a fluorescent microscope where you have two different laser wavelengths coupled into your system, and then you can, for example, image infection here, so that you have a better resolved image with better optics, and also the ability to change the filter set here, completely autonomous, and place that again in the incubator so that you see the infection process while it's happening. So you see some bacteria here, E. coli, that are labeled blue with GFP, so it's more green, and actin with a membrane dye. What you can also do is super resolution again. So the D-Storm, which actually stands for Stochastic Optical Reconstruction Microscopy. There's a group in Berlin who does it right now. So this also shows that the plastic components are actually very stable. So you have usually these experiments where you have the blinking, what you eventually see here. It usually takes easily like 10-15 minutes. And the system is still stable enough to reconstruct the data. You can also do structured illumination microscopy. I think that's maybe where you know Rainer Heinzmann from. So what you do here is you have a laser, you have a small DMD, which is a small display, and you kind of project the structure you address here on this little display. It's a small mirror display into the sample plane. And then from this Moiré effect, so you see some small structures here going or floating over the sample, you reconstruct the higher frequency information from the sample in the reconstruction. And that's what you see here. So we applied the surf algorithm again and similar reconstruction, and you see the microtubule structure much better compared to the wide field image here. And something I'm working on here in Stanford right now, so I'm just visiting Manu Prakash's lab, is light sheet microscopy. That's actually pretty cool technology, since it's relatively easy to build, and you can do all kinds of cool 3D imaging with that. And just to show you what is possible already, so you have, I think, many different technologies and setup configurations. I think Emmanuel Rion, he's the gatekeeper for abbreviations. So there's the OpenSPIM, obviously, there's FluidSPIM, I'd call it OpenEnd Spin, and there's a new technology what we just developed here. It's called the Holy Sheet. I'll give you a little tour how that looks like. So if you ever want to recreate one of our setups, this could be one way of doing that. So you print out all the different components, and then you place that on this so-called template. So this is usually used in schools to motivate students that optics is actually not very difficult at all. So at least in the world we are living in. And so then you have your laser. It's forming a light sheet here with the cylindrical lenses propagated or projected into the sample plane, and then you observe the excited plane with your camera from 90 degrees perpendicular to it. And then the second setup, where you have a capillary that's oriented 45 degrees with respect to your detection lens and the light sheet lens, is very nice, because then you can have flow through configuration. That's cool because our goal is to image plankton, and you can just sample tons of samples through the light sheet and image that over time, and so you get a 3D stack over time. In this case, it's a bit boring, so it's just some beats I labeled very poorly, so you see lots of background, but just to see the principle. So the 3D information, imagine these are plankton, are then gathered over time. Another approach would be to just blow the sample into the focus. So it's the same approach. You have a capillary that's supported with a small pump, and then what you see here are algae, and you reconstruct the sample again as a function over time. So you can continuously image 3D information. It's very fast. And that's something we were working together with people from Roscoff. And then the newest configuration, as I said, it's Holy Sheet. So this works the way that you have two different cameras. One's detecting holographical information. So you have an inline holographical setup here, and you have a light sheet that's created with a Galvo scanner. And so you have many different components here to address with your image or your microscopy control software. That's actually yet another problem to solve. But what's cool here is we have developed a small module. I think that's also where UC2 is very powerful, where you can rotate your capillary. And then, well, this is one of the very, very first results. So now it looks a little bit different. But just to show you that you don't always need to reinvent the whole wheel when you just need to update a small part. So this is just one use case where UC2 is really powerful. And this is then how it looks like with, again, these rather large beads. So every bead is between 50 and 100 micrometer. And so this is the fluorescent response. This is the holography. And ideally, what we want to do is we capture the sample whilst floating through the capillary and also rotating, so that you capture tons of 3D information both from the scattering, so non-fluorescent or non-labeled, and the labeled version, and then match the two together. These are like the very first with algae. We just captured during plankton tow in Monterey around the corner here. And so I think there's definitely more to come. So this is, well, not the very best, but it's getting close to something where it's becoming actually useful. So on the left-hand side, you see some algae that have been captured while flowing and while rotating, and applying some image reconstruction to end up on a 3D plane on the right-hand side. So I think, yeah, there's definitely much more to come, also in terms of data processing, since you capture tons of terabytes per hour and you somehow have to keep track in order to just capture the information you want. Right, so other things we were working on recently was also the integration of an automated lab. So together with Richard Bowman and Wei Wang, we tried creating a feedback loop where you have the sample preparation, the imaging, the image analysis, and also maybe the decision making that leads to new protocols for the next biological experiment. And we centered that around the OpenTrons. So OpenTrons is an open source pipetting robot, and you can easily interact with that using Python, for example. That's very nice because all our algorithms run in Python. And so we just started with something very simple, at least for people like me who do not have many experience with biology. So we just took some yeast from the supermarket and tried different experiments in order to increase the growth rate. And so what you do is you change the concentration for the sugar and the peptone. And that's what you see here on the right-hand side. So we built a small module that scans the well plate after it's getting feeded by the OpenTrons. And then based on the image processing, you count the cells and then go to this very well that has the highest growth rate in the end. And ideally, since everything, like from the microscopy control, the image processing, and robotic control is inside one Jupyter notebook, you can easily share that with collaborators. And in best case, if somebody has the same setup, the result from the experiment would be the same. So one thing we are always trying to emphasize there is like increasing reproducibility so that people really have access to the same methods. And so a few other things we were trying to work on right now is also instead of the optics, making the electronics a bit more modular. So we just started creating a request in the community, so ask for people's needs so that we incorporate that into our design here. So it's definitely a process where we try to come up with a solution that fits most of the needs. So that's how it looks like right now. And we make use of also available tools. So in this case, it's called REST API. So you can interact with the electronics through Wi-Fi. So it's a bit like Internet of Things, or through serial, and also from many different clients. That's very nice. So that you, for example, can use this software called ImpSwitch. It's centered around Napari as the image viewer. And from there, you can control all kinds of different microscopy components like steppers, LED matrices, and also the galvos. And so this is a work in progress where we just try to make the electronics also a bit more user-friendly. And yeah, with this, I think I would like to almost end my talk with lots of talking, just to emphasize a bit on the openness of our project. So we started this project roughly 3 years ago out of the idea to build an incubator-based microscope. And since then it grew constantly, and it's really nice to see that people now start adopting our optics stuff and base their research on it. So it's I think for those who are not that familiar with open science and open source, it's actually not that dangerous to publish sources early, even without proper publication, because people can just build on top and make use of your research. And I think that there's nothing better than collaborating over distance, for example. And so we have many people around the world adopting our sources, and I think that's very motivating to keep on going. And the next few steps definitely somehow be able to scale up our research so that more people can benefit from the optics. That's actually not always so easy due to bureaucracy. And also maybe the next thing would be to create a platform to unify all the different open source, open science, open microscopy projects, because there are so many out there, and it would be just very nice to create better links, thinking about the gap that's created. And I think there's a way to fill it. And also then thinking about more about the research regarding the virus. I think the pandemic has shown that these tools are very important, so that we have to be prepared for whatever comes next. And so the whole field about virus imaging is definitely something we want to tackle very soon. And with this, I would like to end my talk. And right now I'm in Manu Prakash's lab right here and I'm very lucky to visit the groups. Very, very much fun. And next week I'll be back in Germany in Rainer Heinzmann's group. And I'm very happy to work with our UC2 squad here. So I'm just waiting for a question in the chat. If you have any other questions, feel always free to reach out through GitHub. I think you can directly go to our website. After going to this link, just write an issue, write us an email, or I would be very happy to get to know how you can maybe use UC2 for your research. All right, and I'm just observing the channel, this chat. Okay, I think now I understand. So Brice told me that the screen was cropped. Okay, that's unfortunate. I still hope that he got the information. I'll share the slides so that everybody has access to it. I'm very sorry. Just see that now. All right. Yeah, so I'll share the slides and send it around so that everybody can see it. Okay. Well then, I think I will then stop the talk, and thank you very much for being with me here. No, there are some questions. So I'm not 100% sure how to change the well, you can only see a fraction of my screen. That's a bit unfortunate. How can I change that? Okay, I post this link in the, so if I make my screen very small, then you can just see what's useful. So if you go to GitHub, open UC2 and then UC2 Git, or let's make it a bit easier, UC2.org. then you will see a bunch of different components. And I think Barbara Marsikova gave a very nice tutorial on how to start with UC2. So if you give it a chance, just start with the start tutorial. And but maybe if you want to have a deep dive, you just go to the applications, for example, and there's let's say the Incubator Microscope. And what you see there is, of course, again, little documentation here and there, and also bill of materials, so everything you need, for example, the objective lenses, the camera, etc. And then also the where is it? The UC2 configurator. So we give you an idea how to assemble it, and the configurator. There we go. That's a small web app where you, for example, select the Incubator Microscope, and it lists you all the different components necessary to print in order to end up with the microscope. And we always encourage you, so if you have any problems, just reach out to us, and then we can try solving problems together. I think it should be ideally self-explanatory, but if this doesn't work out of the box, just feel free to reach out. So that's one way of doing that. I'm just going back to the GitHub page. And if you go to the root folder again, and then cat, you see all kinds of modules. So I think there's also a list with pictures. So you have the base cube, you have different cameras, and you also have mirrors. And so you can select between different components or modules that are visible. So for example, we have an updated multicolor. I just updated it yesterday so that you can replicate the multicolor fluorescent microscope with 2 different lasers and filter switches. What you can see here, for example. And usually we really try to give all the instructions so that you can really replicate whatever is up there. So if there's something missing, which is very likely, just ping us and write us. So that's at least the 2 ways right now. There's also many, many more modules around the whole GitHub repository. So if you just go to GitHub/OpenUC2, you will see a bunch of repositories. So for example, the UC2 RES is the electronics development, where we try to work on the software. You can just stumble around and maybe find some cool new features I am not even aware of. So for example, the UC2 Feather is the electronics, which I think right now is not perfectly documented. Oh yeah, well, it's going somewhere. Okay. Just going back to the other, because my YouTube on my phone does not show the questions. There it is. No. Okay, I think I should have studied YouTube a bit more. So, there. Yeah. Okay. There are no more questions. I will just send the PowerPoint presentation so that it becomes available. And thank you very much for listening today. And I'm sorry for the inconvenience with the screen size. I didn't know that this is even possible. I'm very sorry. All right. Thank you very much and have a good day. Bonne soirée.